Good morning, students. Welcome to the class on advanced organic reagents. In this class, we will discuss about tributyl tin hydride reactivity. What is tributyl tin hydride? Tri-N-butyl tin hydride. We can also call it as organostannate. Tributyl tin hydride, or in short, we can also call it as TBTH. Tributyl tin hydride. Tributyl tin hydride is generally used for the reduction of alkyl halides or alcohols in a radical fashion. We will see how we will perform this reaction. TBTH in presence of a radical initiator. TBTH on its own cannot react. In presence of a radical initiator, the halogen can be reduced. So hydrogen from TBTH will be transferred to alkyl halide, and this halogen will be taken away by tin. We can use any radical initiator, either AIBN or hydrogen peroxide or dialkyl peroxide, whatever it is. We need just a radical initiator. We will look at the mechanism how this reduction of alkyl halide occurs. In presence of a radical initiator, of course, we know AABN, when it is heated or under photochemical conditions, it will be generating a radical like this, right? So this bond also, one of the radical will be polarized towards this carbonyl. So we will be generating isobutyronitrile radical plus nitrogen gas, it will be escaping. We will consider this as initiator radical. Initiator radical. Then initiator radical reacts with TBTH and it takes the hydrogen from TBTH. This is the initiation step, and this is the first step in the propagation of this radical reaction. Then what will happen? Tin radical will be generated, and then initiator will pick up that hydrogen from tin. So with this, initiator part is over. Okay, so we need a very small amount, maybe 1 mole percent or 5 mole percent of the initiator. Then what happens? This tin radical will pick up the halogen from the alkyl halide. Tin radical will pick up the halogen from alkyl radical. So to avoid confusion, I'll write like butyl, Bu. So I'll write butyl. Tin radical will pick up the halogen. So there is no radical. There is no radical. Tin radical pick up the halogen from alkyl halide. Then R becomes radical. After generating alkyl radical, the alkyl radical now takes the proton hydrogen radical from TBTH. See from this step, initiator picked up the proton hydrogen radical from TBTH. So tin radical is generated. Tin is having good affinity for the halogens. So tin will take the halogen from alkyl halide. Alkyl radical is generated. Alkyl radical will pick up the hydrogen from TBTH. So alkyl halide is reduced to alkane. Then again tin radical is generated. So this process continues. This tin radical again picks up a halogen from alkyl halide. Alkyl radical will be generated. So this process is a cyclic process. It continues. I'll give you some examples. Adamantane bromide, when it is treated with the TBTH, hexane under photochemical conditions. Under photochemical conditions and radical initiator, what is the product? What is the product? Just remove this halogen, that's it. Here the halogen is chiral, it is on a chiral center. Write the product. Though it is a chiral center, it doesn't matter for us. Just remove this halogen and replace it with hydrogen. The alpha functional groups may not involve in this reaction. When we have a mixture of halogens, both chlorine and bromide, then TBTH is having good affinity for the chlorine. So removal of chlorine will be the major product. It is 2.5:1. Removal of bromine is a minor product. The beauty of TBTH reductions of alkyl halides is that we can use this reactivity for cyclization. So cyclic compounds can be generated under the similar reaction conditions. When a radical is generated here, it will undergo intramolecular cyclization with this. 1, 2, 3, 4. Generally 5-membered rings are more stable compared to 6-membered rings, but 6-membered ring will also be possible if this radical combines with this compound, with this carbon. 1, 2, 3, 4, 5, 6. So major is 5-membered formation. This is the double bond. Minor is the 6-membered ring. So under similar radical conditions, if a double bond is there, then we can go for intramolecular cyclizations. This is a 5-membered ring. The same reaction conditions were utilized for a tandem cyclization process. You see here, when we generate the radical initially here, it will undergo cyclization with this double bond. Radical and one of the electron in this double bond, they will undergo cyclization when we count the ring size 1 2 3 4 5 membered ring. Then this generated radical will further undergo cyclization with this triple bond. As I said, 5-membered ring formation is more stable compared to 6-membered. So this will undergo cyclization with this with this carbon. When we count the ring size 1, 2, 3, 4, 5. So this is how we will generate 3 cycles in a single step. We are generating 3 cycles in a single step because this hydrogen is below the plane. The other side also the hydrogen must be below the plane. Since this ring is like this, the other ring will be opposite. So that means the two hydrogens will be above the plane to have minimal spherical repulsions, because only one double bond is undergoing reaction in cyclization, other two double bonds. So triple bond is converted to double bond. So that means we can have tandem cyclizations. Only thing is we need proper functional groups placed at proper places. This is called linear triquinane. Not only this, so far we have seen only intramolecular cyclizations. It is also possible to have intermolecular cyclizations. In this case, see, when we generate a radical here, the initial generated radical will undergo bond formation with this double bond. So there will be a bond formation between this carbon and this carbon. Then the radical generated on the other side now undergoes cyclization intramolecularly. When we generate a bond between these two carbons, they become intramolecular. So intramolecular cyclization occurs here. So first coupling, then intramolecular cyclization that generates two fused 5-membered rings. One 5-membered ring is already there. We are generating the second 5-membered ring. Triple bond is converted to double bond. Of course, as I said, this ring fusion will always be cis in this case, and we have two nitrile groups. So that means we can have intramolecular cyclization, a tandem cyclization, or coupling followed by cyclizations. The cyclization is possible with the alkene. Not only that, the cyclization is also possible with carbonyl. When this compound is treated with TBTH, sorry, what will happen? The initially generated radical, it will undergo cyclization with this carbonyl. So it generates a fused cyclic system. Count the ring size 1, 2, 3, 4, 5, 6. Of course, it generates a radical here, right? So radical will couple with this, then one of the electron will be polarized towards oxygen. Then this double bond, this carbon-carbon bond will break down. It will polarize one electron that side, other electron this side, so that it generates, it regenerates the carbonyl and it forms CO2. So that means the ring expansion has been occurring here. Not only TBTH, we can also use silyl hydride. This silyl hydride can be used for the same transformation. Okay, you write the product silyl hydride. This silyl hydride can be used for the same transformation. Another important reactivity of TBTH is that TBTH will react with triple bonds, so that one side hydrogen will be added, other side tin will be added. So we are getting allyl stannins. Sorry, this is vinyl stannine, right? Vinyl stannine. So a triple bond will be reduced to vinyl stannins. This, of course, this can be explored in different ways.